To rationalize a denominator is asking to eliminate the irrational number that's in the denominator. To do that, in this first example, we want to eliminate this irrational expression, square root of 3, from the denominator. It's not a perfect square. For it to be a perfect square, we would need another 3. To maintain equality, we will multiply the numerator by square root of 3 so that we have essentially a 1 that we're multiplying this expression by, which doesn't change its value, but results in 1 times square root of 3 in the numerator and a perfect square in the denominator. We end up with the square root of 3 times 3, or 3 squared, which is 3. We now have a rational denominator and no longer that irrational square root of 3 in the denominator. In this next example, to rationalize the denominator here, let's use the quotient rule for square roots and break the square root of this rational number into the square root of 5 over the square root of x, since we can't simplify it as is. This results in an irrational number in the denominator. Square root of x cannot be simplified further, but to rationalize the denominator and eliminate the radical, we would need another x underneath the radical. So I'm going to multiply the denominator by square root of x. To maintain an equivalent expression, we'll multiply the numerator by square root of x as well. This special 1 doesn't change our value, but it's going to alter its appearance. And simplifying, we have square root of these two radicals is the same as the square root of the product of the radicands. And in the denominator, square root of x times square root of x is square root of x squared, which is x. We have now rationalized the denominator. In other words, we've eliminated that radical from the denominator. Sometimes it's easiest to rationalize a denominator after the expression has been simplified. So if we look closely at this next example, we have square root of 50. Square root of 50, using the product rule for square roots, can be expressed as the square root of 25, a perfect square, times the square root of 2, since these radicands, 2 times 25 is equal to 50. We now have 15 in the numerator. Square root of 25 is a perfect square of 5, and we'll leave the square root of 2. Looking at our rational expression, we can reduce this. We have a common 5 in the numerator and the denominator. 15 divided by 5 is 3. 5 divided by 5 is 1, leaving us with 3 over the square root of 2. We have an irrational number because of that square root of 2 in the denominator. To rationalize the denominator, just as we've done in the previous two examples, we will multiply by an expression that will give us a perfect square. We have 1, 2. We need a second square root of 2. To maintain equality, we'll multiply the numerator by square root of 2, since this expression is 1, and multiplying by 1 doesn't change the value. Multiplying in the numerator, we have 3 times the square root of 2, and in the denominator, square root of 2 times square root of 2 results in square root of 2 squared, or square root of 4, which is 2. We now have a rational denominator in its simplest form. In this last example, we cannot simplify either one of these square roots, and expressing it as a single quotient underneath one radical sign doesn't allow for any common factor to be canceled out, so the only thing left is to rationalize the denominator. Here, for this to become a perfect square, we not only need a 2 as a radicand, but we will also need a y. Square root of 2y times square root of 2y will rationalize itself and be a perfect, because it's a perfect square, but to maintain equality, we'll also multiply the numerator by square root of 2y. Using the product rule, we'll multiply the radicands together underneath one radical sign, so we have a 14xy in the numerator. In the denominator, we will have 2y times 2y, or the quantity 2y to the second power. Anytime you have a quantity to the second power and taking the square root of something squared is that term. So we've rationalized the denominator, and in the numerator, we could see in its prime factorization, there's no perfect square here, so we'll leave it as 14xy in its simplest form with a rationalized denominator.